All right, welcome back to CS50. This is the end of week 4. So if you haven't already, do pull up or follow along while I do here a simple Google search for this keyword recursion, which we discussed last week. And do you get it? OK, so many new jokes available to us now. So someone has a sense of humor on the Google humor team, right? All right. What a bunch of dorks now. All right. So a couple of recaps and announcements. So last time, recall that we focused on algorithms and actually solving some problems a bit more efficiently. And we started to use this so-called asymptotic notation, just big O and omega. And there's also theta, but we'll focus mostly on big O and omega. And just to toss some jargon out here, know that we focused a lot on big O of n, linear. And so linear perhaps brings back memories of the straight lines that we do while graphing. We looked at big O of n squared, bubble sort, selection sort. These were in big O of n squared. And we found that that was generally slow. It definitely felt or looked slow when we compared it to something faster, namely n log n. Now, frankly, most people don't tend to say supralinear, but it is an apt word. But n log n was kind of a sweet spot between n squared, which was really slow, and n, which was generally unrealistic, at least thus far for doing something like sorting. But know, too, that anytime you have an algorithm that takes the same amount of time, irrespective of the size of the problem, irrespective of the number of students in the room, irrespective of the number of inputs provided, well, that's what we would call constant time. And just as we cross out things like divided by 2 and times 2, anytime you want to express the notion that an algorithm runs in constant time, 5 seconds, 10 seconds, no matter how big the input is, you would typically say big O of 1. Well, what's an example of a constant algorithm? Well, I mean, you can think of something simple like at the start of lecture, rather than taking something like attendance, the algorithm can be greet students. So I execute that algorithm, hello. Like no matter what, that's going to take constant time. Even if I say 3 things like hello, class. OK, so that's 2 steps. But again, we get rid of these constant multipliers, so it's still constant time. We saw binary search with Sean up at the board on video, where log n was the ultimate conclusion there. But know that there are other things. Sometimes you even can't do n squared. The problem's just too big or too complex. So you might have to have something polynomial, n raised to the something power, where that something, call it c, is bigger than 2. And really bad algorithms are things that are in, say, factorial, n a factorial, which we'll typically avoid. But there is the potential to write algorithms that really are that slow. And then exponential is yet another one not even depicted here, and that too tends to be quite slow. But today, we return now to the practice of actually coding things and understanding what's going on inside of a computer, and peel back a layer called pointers that is both empowering, as we'll see, but also quite dangerous. So if you don't recall, Wi-Fi should now be available here in Sanders. So a little teaser before we move on to some milk and OJ here. So this was a little video that should tease us as to today's focus, this topic of pointers. In a nutshell, a pointer is going to be an address, the address of something in memory, but we'll see what damage we can actually do if we use these things incorrectly. So a clip from a certain Stanford University computer science professor here.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody!
That's all you get right now. We will conclude with the follow-up there. It's just fun to imagine Nick, this esteemed computer science professor at Stanford, kind of playing at home with his clay models and recording himself do this. So more on that later today. So recall that we ran into some problems early on when we tried to do something so simple, like swapping variables, and writing our own swap function also failed ultimately. And so consider how we solved a problem like this. I'm going to get rid of things like ints and chars here, because we can just generalize with pseudocode. But here might be 2 variables, a and b, and they've already been initialized to be orange juice and milk, respectively. Well, suppose that the goal here is to swap the contents of a and b, right? And sort of intuitive terms, the goal is to put this over here. But obviously, if you take the straightforward approach that kind of looks at first glance correct, B goes into A goes into B, of course, you get a bit of a mess. If this is A, this is B, and you try doing, that is disgusting, this, right? There's no way I'm going to be able to move just the white stuff back over here onto the left. And so, right, this is buggy, right? Broken algorithm, if that weren't clear already. So how do we solve this, perhaps, in the real world, obvious problem? Right, so you have some kind of temporary variable. So if we introduce, for instance, just an extra 32 bits or whatever the data size is, then we can actually fix this whereby, let's try this again, whereby we have a fresh cup of A, a fresh cup of B, and then we're going to need, whoops, let's not do that. All right, fresh cup of B. So now we need, of course, a temporary variable. If there's any suspense, really, we should know where this is going, right? So we have A with orange juice. We put A into temp. OK, that was productive. Now we have B going into A. So that's over here. Little cross-contamination, but not nearly as bad. And now temp goes into B. All right, so this is kind of a fun game, right? We could do this all day. But thank you. Thank you. So not bad. We've solved it. But then we broke this, right? You could implement something like this, albeit in C, in a function like main, and it would actually work. So you could swap two variables, A and B, if they're integers or whatnot, and it would work in main. But then we kind of got arrogant and introduced our own function, swap, whereby we pass in A and B. And we claim this is good practice, right? You factor out sort of conceptual chunks of code into functions that are aptly named. We slap the label hierarchical decomposition on it. But then this broke, this simple thing of swapping. And what was the simple answer as to why the inputs to this function are not, in fact, swapped once this function executes? Yeah, so it was this issue of scope. When you pass in two variables, say x and y, into a function like swap, what's actually passed in is two copies of those things. So what's really been happening in the case of an actual swap function is if this is, say, x and y, and these exist in main, well, when you actually call swap, what happens is, I'm going to have to do a little bit of magic here. So if this is x, this is y, this is going to be A, this is going to be B, what actually goes into this cup? Right, it's a copy of whatever x is. So it wouldn't really make sense to pour this in here just yet. So I'm just going to cheat and say this is a copy, which pretty much is, half a glass of orange juice. Y goes into B, so we have a perfect copy of this. And then what happens in this swap function? Well, the swap function, again, is actually correct. We have this local temp variable. So we go ahead and move A into temp. Then we go ahead and move B into A. And then we go ahead and move temp into B. And this is all working really well. And then we return. And what happens? Well, the slice of memory that was allocated to the swap function is effectively gone. I mean, it's actually still there, but the computer just forgets about it. So if you kind of fast forward, if we ever call another function, we might end up with orange juice or milk by default in those new variables just because of those remnants. So there actually is something still here in memory. But now we have x and y. We didn't really do anything. So how do we actually solve this? Like, just kind of intuitively, if the swap function isn't so much a function, but rather it's just a friend, and you want to hand your friend x and y, and you want that friend to swap x and y for you, what should you really be handing your friend? Yeah, so ideally you just hand him or her the actual cups, the originals, x and y, and let him or her do their thing with an extra temp variable and actually do the swap. So how do you actually hand to a function the original x and y? Well, what you can do is this. If you have a little scrap paper and you say to your friend, all right, well, let's suppose now that, actually, this isn't unrealistic. Suppose that x and y are kind of bolted to this table in the same sense that a variable x and y are in one place in RAM, right? The variables aren't going to move. They are where the computer allocated them in RAM. So what I can do is I can't really hand my friend these variables because that would be to move them from memory. But I can say, you know what, dear friend, the OJ is at location 1, 2, 3, 4 in RAM, and the location of Y is at 4, 5, 6, 7. I'm just making these numbers up. So what you hand your friend is not X and Y, but rather this little cheat sheet, the address of x and y, so that when your friend receives this, he or she can say, all right, the x is apparently at location 1, 2, 3, 4. So I need to swap these cups for David. So I'm going to allocate my temporary variable, TMP. I'm going to go ahead and bring it with me to location 1, 2, 3, 4 in memory. OK, I'm going to go ahead now and pour that location's contents into the temporary variable. Now what am I going to do? All right, I need to now go to location 4, 5, 6, 7. So I go there, I find it, and I realize, oh, OK, I'm going to move its contents to that same temporary variable. And then what do I have to do? All right, well, now I have to go back to the original cup and actually say, all right, now I have to move the I got completely lost. What goes next? Orange juice goes next. I have to take those contents, move it over, and if I didn't completely screw up this algorithm, they are indeed swapped, but they're swapped at the original locations because I actually followed this map, if you will, to my friend's cups of OJ and milk, changed those values, albeit with the help of my extra temporary cup, and then the original contents are changed. So on the one hand, I'm saving memory in that I'm not making copies of milk and orange juice this time, but I am spending some memory. What am I spending in this scenario? Whatever the cost of these pieces of paper are. So it turns out inside of a computer, these little slips of paper will cost you generally 32 bits. A pointer, otherwise known as an address in memory, will cost you 4 bytes or 32 bits, at least on many computers, including the appliance. Now, if you're familiar with your own personal Mac or PC being 64-bit Intel inside, well, that actually means these slips of paper are twice as long. You can fit bigger addresses in them, and so pointers can also be 64 bits. And on hardware that's 10 years old, 20 years old, 30 years old, you might have pointers that are just 16 bits or 8 bits. But that's all it is. A pointer is just the address of something in memory, and so this seems to now solve the problem. We can just inform someone where these things actually are. So what's this going to look like? Well, this is before. This is the broken version of swap. But the after version, if I now spoil this here, is going to be that. So we have to introduce a little bit of more syntax. And there's actually one tweak we're going to have to make to main. But if we want to rewrite our swap function so that it does still swap, but it swaps correctly by passing in the address of x and y, or whatever the inputs are called, and actually changes them at their original locations, we essentially have to introduce some of these stars, these asterisks before the variable names. So we'll tease apart exactly why that is, but let's now just toss out a bit of jargon so that when we start seeing these things on the screen, it's not